In this lecture, we started to discuss what is adele space, but before talking about what they look like, let me give some notions. Let me remind you some notions from section 1.4. Particularly for this notion, we follow two main references. The first one is our main reference from Stettenot, and the other one is the Sutherland's lecture notes on Introduction to Arithmetic Geometry. And let's recall that our first main motivation indeed to understand the Riemann-Roch theorem more properly, particularly for given divisor, our main purpose was to compute the dimension of its Riemann-Roch space explicitly, but the first step to understand its dimension was to show it was finite dimensional. And indeed, our first step to see that every Riemann-Roch space is a finite dimensional vector space, we observe for two divisors, A and B, one is less than or equal to, with respect to partial order on the divisor group, we get subspaces of the Riemann-Roch spaces, depending, like in some preserving the order. And the dimension of the quotient space, so by the linear algebra, indeed we can write it as the dimension of B minus dimension of A, is less than or equal to the difference of their degrees. And let me also briefly recall its proof. By this assumption, indeed, it will be enough to see the inductive step. I mean, the proof works over the induction, and indeed, first we suppose that B can be written as A plus B for some place P, and indeed, we can choose a uniformizer of this place P, and we can write VP of B as VP of A plus 1 in this case. And let me also denote this integer by n. So we denote the valuation of the divisor B at P by n. And by using this setting, we introduce a map from the Riemann-Roch space of the divisor B to residue class field Fp, which is determined by this specifier P, which maps the functions in L of B to evaluations by multiplication T to the n at P. So this definition makes sense. Probably in previous lectures, when I was talking about this lemma, I introduced this function, and even in Stettenot, this function is introduced by T times X, but I think it's supposed to be n, which is like explained in the second reference, because in this case, this definition makes sense. Because if you consider the valuation of this function T to the n times X by the properties of the discrete valuation map, indeed we can see that this valuation is going to be always positive. So that means this image cannot be infinity. So the phi is here, so the image cannot be infinity. So this definition makes sense. And we can also easily check that phi is k-linear. Please check. And we have also seen that the kernel phi is equal to Riemann-Roch space of A. So if you don't recall, it's probably we will discuss it in the discussion session. And by the first isomorphism theorem, we can wave this quotient as a subspace of the residue class field, and we know that both of them are the vector spaces over K. And since the residue class field has finite extension degree, and this is also defined as the degree of a place is always finite, we can conclude that indeed this dimension is less than or equal to degree of P, and the general case follows from induction over P, the number of the places P which appears in the sum. And indeed, let me note that this lemma can be rewritten also like this. So in general, for any divisors A and B, their dimensions and the degrees always satisfies this inequality. So the question is that when do we have equality, or when do we have strict inequality? So when for which pairs of divisors this bound is tight? And in order to understand, let me again consider corollary 1.4.12, particularly part C, which tells us for when degree 0 divisors are principal, indeed, as we have seen this corollary, if A is principal, if and only if its dimension, the dimension of its Riemann-Roch space is 1. So this expression means that, so that means if A is principal, L of A is equal to 1, and L of A is equal to 1, means A is principal. But if you particularly consider the contrapositive statement of this last statement, we can conclude that if A is not principal, then the dimension of its Riemann-Roch space is going to be 0. So that means, indeed, if, for instance, if you consider degree positive divisor, if you consider degree 0 divisor, if it is not principal, so in this case, since its dimension is going to be 0, we can't get this equality. So in this case, this bound is not tight. So more explicitly, we can say that if we consider the Jacobian group, which is the quotient group of the 0 divisors over principal divisors, so whenever this Jacobian group is not trivial, that means there exist degree 0 divisors which are not principal, whose dimension is 0, and this allows us to see that indeed this bound cannot be sharp or cannot be tight. So the reason of not to be able to get equal to always is that this k-linear map we consider is not surjection. So in order to understand what kind of vector spaces, finite dimension vector spaces has dimension or can be written as the difference of the degrees of two divisors, we need to introduce the notion of the adele space as we will see in the next video.